Hello students, how are you? Good evening. So I'm Mitosh, also known as Dr. Stone. Okay, well, if you know that anime, you will know why my students call me Dr. Stone. So here we discuss concepts of chemistry that's there in the syllabus of JE and NEET. We try to take a concept, we take a concept, then we simplify it into very understandable, simple language definitions and interpretation, and I club it with real life analogies, and we ended up with some questions like PYQ questions from NEET, JE Mains, J Advanced, and teach you the applications of those concepts. So when we discuss a concept here, we make sure we go from the basics, right? And we make you understand, or we make you equip or master that concept so that you can do the questions that may come in NEET, JEE Mains, or J Advanced. Okay, very good. So today, under our microscope, we have a topic which a lot of students find difficult. So you have a chapter called chemical bonding, right? A very important chapter, super important chapter for physical, inorganic, and organic as well. Lot of concepts from chemical bonding get extrapolated and reused again in other chapters. Cool. So it's an important chapter, and in that we have this topic. It's a small topic. Video will not be very long. It's a small topic, but it's highly conceptual topic, and a lot of students misunderstand this and they make a lot of mistakes in the exam. And from this particular topic that we are going to discuss, there comes a lot of questions, because every higher level questions in the first part of chemical bonding will be related to this topic. Well, without further without further ado, or a lot of, I already hyped up the topic so much. So the topic is Ben's rule. Cool. Ben's rule. Well, as the name suggests, it is invented by Mr. Bent. But as you know, for JE or NEET, it's not about memorizing who invented what and etc. It's about the concept, right? The critical thinking, application of concept. So this you don't have to learn anyway, because Ben's rule, the name has who invented it, right? He was very forward with it. So Ben's rule, let's see what is Ben's rule. I'll just give you the basic definition of what is Ben's rule. Then I'll take some example and explain how this works. Okay, that is the most important part, because I understand most of you would have memorized what is Ben's rule, just the definition, but the understanding of the Ben's rule, the application of Ben's rule is where you have trouble, correct? So yeah, before going into Ben's rule, one thing, what is a prerequisite for this topic? I told you we will go from basics, but as we cover each topic in one video or something like that, one session, so there is a prerequisite for this topic. There are certain topics that you already should know and mastered so that you understand Ben's rule. So prerequisite for these topics are obviously the first part of chemical bonding, very basics. So you should know hybridization very well. Hybridization, very important for this prerequisite, very important prerequisite. VSEPR. Actually, Ben's rule is an addition to VSEPR. Ben's rule is actually what comes after you're learning basic hybridization and VSEPR. Also, it will help if you know about electronegativity. Okay. Electronegativity. Well, I assume you have already learned. If you are searching for Ben's rule, I assume that you already learned all this, right? You have a very basic idea. Okay. So these are the prerequisite. So if you are not aware of any of this topic, I suggest you go and learn, or first you master these concepts, then come back to Ben's rule. But I'm assuming, since you are here till now, so you're assuming you already know these topics. So let's see what is Ben's rule, right? Ben's rule, a very important definition. So Ben's rule, I'll write it with another color pen. So Ben's rule says when a central atom makes bonds with, so as you I mean, it goes without saying, but benzol is part of hybridization, after the hybridization VSEPR. So I hope you understand, we are only talking about the covalent compounds, right? I'm not going to mention it again and again. So makes bonds with multiple side atoms. This is very important. Multiple side atoms. Multiple side atoms meaning more than one type of elements making bond with central atom, right? Multiple side atoms. More electronegative values, En, electronegative side atom will choose to bond with less percentage S character orbital of central atom. Very simplified definition. Okay, so what are the important points in this definition? When a central atom makes bonds with multiple side atoms, okay, then more electronegative side atom. This is a very important point here. More electronegative side atom will choose to bond with less percentage S character. So more electronegative, less percentage S character orbital of central atom. Okay, so you write it down, right? Keep this in mind. You repeat it multiple times. Keep it in mind. When we go through the explanation of the rule and example, you will understand each and every line. Okay, cool. So I'm assuming you already written it down. So I'm going to rub this off. Okay, wiped it down. Now let's see. So how does this or why does this work? See, let's take an example and explain. Okay. Or before that, I'll explain the connection between percentage character and electronegativity. Okay. So percentages and electronegativity. So it's about the electronegativity of that particular orbital. You know what is percentages, right? Suppose for sp3, what is the percentages? Percentages is how many orbitals are there? 4, and out of that 1 is S. So 1 by 4 into 100 because it is percentage. So 25 percentage S character and 75 percentage P character. Right? Now we know S orbital. Okay, S orbital. What is the difference between S orbital and P orbital of the same shell? Right? So I'm writing NS. Okay, and I have a P orbital. So we have NP. Okay, NS and NP. You see, NS and NP, which has lower energy. So if we talk about, let's say this has lower energy, right? Because energy is N plus N. Higher energy. Now next, so lower energy meaning closer to nucleus. This is farther from nucleus. Okay, cool. Now next point is very important, right? This is more round shape and less long, not long, I'll write less lengthy. I'm using these words so that you get a graphical understanding of this. what we are going to discuss. This is more slim shaped, and longer. Okay, so what I'm trying to tell you is, see, s orbital is like this, spherical, p orbital is long, dumbbell shape, correct? So when we hybridize both, hybridization meaning we mix them together and reshape them. If more s character meaning it will have more round shape and less length, right? So it will be like this, and let's say like this. But if more p character meaning it will become thinner, because that is the nature of the p orbital. S orbital is more round, so it will become longer as well. Clear? Okay, so yeah, so I hope you have written it down. Now I'll make a graphical explanation of different orbitals and give you an idea about this. So I hope you have written it down. Okay, percentages character is something you already know. With percentages character, you get a graphical understanding of how an orbital will look, right? So if you check, let's say we have SP, we have SP, SP2, SP3. Okay, we have SP, SP2, SP3. So what is a percentages character? If you check the percentages character, so if I write percentages, this is 50, this is how much? This is 1 by 3. So 33.33, wait, 334 you can write that out. Why do you know? And this is 25%. Cool. So this has more percentages character. So how will this look? This will look like it will be more round. I hope this is clear to you, right? You already know how this will look. Okay, it will look like this. Now what about SP2? SP2 will be little more slender and longer. So you will have something like, what is the shape of SP2? SP2 you have, I'll just express one orbital because for SP3 we'll have to draw the whole geometry. So I'll express, okay. Just drawing one orbital. Okay. What about SP2? SP2 one orbital will be little more longer. Right? Look at this. This is little longer and slender. It's not as round as this one. Okay. Now SP3 I'll draw here, right? So you have, obviously it will be something like this. Okay. Pardon my drawing, but I'll try to give you a figurative understanding. Okay. So this is SP, this is SP2, this is SP3. Clear? See this, see the difference. This is shortest but round, more round. This is longer than SP but not as big, okay, thick. Now this one, it's thinner and longer. Clear? That's how the percentages character affect the shape. Okay, cool. You write it down. Okay, you can pause the video and write it down. Now I'll explain what's the connection between electronegativity and percentages character. Okay, so I hope you got an understanding of the shape or geometrical aspect. I hope you got an understanding of the geometrical aspect of the percentages character. Okay, so now let's see what is the connection between percentages character and electronegativity. Correct? So Now you see, what is electronegativity? Electronegativity is the electron pulling capacity of an atom when it is making bond. So closer the orbitals are to nucleus, more electronegativity, correct? Which is closer, more s character, more closer to the nucleus, correct? So which meaning electronegativity is proportional to percentage s character. Okay, percentage s electronegativity is proportional to percentage s character. So more the percentage character, because think about it, s is in the same shell, s electron is tougher to remove than p electron because s electron is closer to the nucleus. So keep this in mind, electronegativity. Okay, now let's see, now let's think back with the Benz rule, think back to the Benz rule. In Benz rule, let's suppose you have a central atom taking A. It's not representing any particular element, just a basic. So let's suppose from here B is coming, C is coming. Okay, so if electronegativity is C is greater than B, C does not represent carbon and B does not represent boron here. Just for the namesake, I'm just putting arbitrary representation. So if C is more electronegative, what will C try to do? C will try to get the most out of A, right? So let's suppose let's say A is a person. A has, let's say, two seats to a concert, right? 2 seats. One is, let's say, good seat meaning, let's say it's a concert, so good visibility, good seating arrangement, good positioning and all those things. One is good, 2 is moderate. Okay, so A is the person. Now A has these 2 seats, so 2 tickets to these 2 seats, and B and C wants those tickets. So A is ready to give it to B and C, either of the ticket to B and C, right? A doesn't have an issue. But let's suppose I'm trying to connect this electronegativity into, let's say, charm, right? Some people are very persuasive, they can charm. So suppose C is more charming, right? So electronegativity is charm. So if C is more charming, C will get the best ticket, right? Suppose both of them wants ticket, right? They want to go to their concert. Like atoms wants to make bond and become stable. So this C will get the best ticket, correct? The best ticket available, or the easiest ticket or most comfortable ticket, and B will get the second one because that's the only thing left, correct? So likewise, more electronegative element will go to the orbital which is easier to acquire. Which is more easier to acquire? The one which is farther away from nucleus. That's why more electronegative element will, said atom will choose less percentages character orbital, because that is the easiest orbital for any element to make bond, because it is farther away from the nucleus, correct? And also you need to understand, so you might think, sir, what if all of the orbitals have the same percentages character? Now that's where it gets amazing. So what will happen is the atom will reconfigure the hybridization or rehybridize, and it will give less percentage s character orbital to more electronegative element, right? So this is a real life analogy. Now we'll take some examples and that part will become more clear to you. take few examples. Let's see. Okay. So what is one example we can take? Okay. H2 and okay, F2. So we are going to discuss what will be the bond angle between H2 and F2. Correct? See, H2 and S2 both have sp3. Correct? And what will be the shape? Shape will be, so you see, oxygen, it has 2 lone pairs, right? Hydrogen, hydrogen. Here, oxygen, fluorine, fluorine. Right? Suppose this is theta1, this is theta2. Well, you know this value, but I'm just giving you an idea. We don't need to memorize a lot of things in chemistry. Shouldn't we need to understand the comparison and stuff. So my question is, what is the connection between theta1 and theta2? This is not a question that I invented or something. There is a previous year question from IIT 1998 or 1999. I don't exactly remember. So let's see how to do this question, right? So a lot of students, there was an option where, let's see, one option was theta1 equal to theta2. So a lot of people thought, see, same shape, both are bent, right? They thought, okay, there are lone pairs, there are bond pairs, so they should have the same bond angle. But that is not the case. That is not the case. Theta1 is not equal to theta2. Okay? Now let's see. Now, since I have got your attention, how do we do this? Now let's apply Ben's rule and try to do this question. Okay? So you see, hydrogen, oxygen, fluorine, oxygen. So what will happen here is, we have this. So hydrogen is not, what is hydrogen? sp3, right? But the thing is, hydrogen is not very electronegative compared to fluorine. Fluorine is the highest electronegative. So this orbital, or right below, so that these pictures remain, undisturbed. So orbitals chosen by fluorine will have less percentages than by hydrogen. What does that mean? The orbitals, so let's suppose I'm writing this as A and this is B. So A will be longer and thinner compared to B. Why? Because less S character, it will not be round, it will become thinner. If you go back to the graphical representation I made, it will become thinner and longer. Now when it becomes thinner and longer, that means their repulsion will also decrease, correct? Because suppose you had two things like this, so they will stay like this. But if I keep it, if the orbital's electron density becomes like this, what will happen? It can come closer, correct? Because it becomes longer. So the effective repulsion we can minimize. Which meaning, what will be the answer? This can come closer because it is longer and thinner. So theta2 is less than theta1. A very important question and very important explanation of this concept, right? I hope you understand this. So in the next video, or we can discuss one more question, or in the next video we can discuss some few more questions on Ben's rule. Thank you so much.